All right, welcome everybody to the fifth and final day of HoloTubeJunior. So we have our first speaker today, MattiaCesaro, and we're looking forward to your talk. Mattia, go ahead.
Well, thank you very much. And let me also thank all the organizers of this nice event to give the opportunity to us, PhD students, to speak about our research and what we've been doing so far. So what I want to talk to you about today is a Kaluza-Klein spectrum analysis over a certain M-theory solution, which happens to be dual to the cubic deformation of ABJM. And I'll hopefully become clearer about what I mean by this, and also about the so far cryptic title of the talk in the next slides. And let me mention that this is all based on work that I've done with my colleague, Gabriel Larios, and my supervisor, Oscar Barella. So the plan of the talk, we will provide some basic information about set framework. So we will spend some words about the cubic deformation of the ABJM theory, and when it is its gravitational dual, which we will call GMPS for reasons that will become clear later. Then what we will be doing, which is also the body of the work we've been doing so far, is to compute the complete Kaluza-Klein graviton spectrum numerically over this M-theory solution. And then we will see towards the end of the talk that we will also be able to take some steps beyond the graviton spectrum and make some considerations about the full actual spectrum. And we will see that it displays this very interesting phenomenon of space invaders. And then we will just conclude and provide some interesting lines of research to be eventually pursued in the future. Okay, so let me start with the field theory side. We have the usual ABJM theory, which is a superconformal transhumance matter theory with transhumance levels k and minus k. It is dual to a stack of M2 branes on these orbifold singularity, C4 modulos at k. And the ones we're interested in, which is also somehow the simpler case, is the case for which k is equal to 1. Because then the supersymmetry of the theory gets enhanced from n equals 6 to n equals 8, and correspondingly the bosonic subgroup becomes SO8. The field content of the theory can be conveniently expressed in this very nice and compact way by condensing together in a superpotential the four chiral matter superfields, and whose UN gauge indices are properly contracted with some 't monopole operators carrying negative units of flux. Now, we won't dive any further into the topic of 't monopole operators for this talk, also because they are somehow slippery in the theory, but the only assumptions that we were going to take is that they do not carry any R charge. So the only R charge carriers will be the chiral matter superfields. And let me also remark that the superpotential so written is obviously not SO8 manifestly invariant, but only SU4, which is a subgroup of SO8. This will anyhow turn out to be useful because we want to analyze the relevant deformations of this theory, which are n equals 2 and SU3 preserving. So one can implement this kind of deformations by adding to the superpotential powers of one of the chiral superfields, let's say Z4. Where here this writing is of course schematic because the gauge indices should still be properly contracted with some monopole operator. And so the deformation is obviously n equals 2 preserving because we chose a chiral superfield, and it is SU3 because the rest of the three chiral superfields can be rotated into each other, therefore preserving the form of the superpotential. And it happens to be the case that only for p equals 2 and 3 the deformations are not only relevant, but do also preserve unitarity. So for higher P, that happens not to be the case anymore. And by demanding that the superpotential has R charge 2, as customary, then this kind of deformation leads to the infrared R charges for the triplet, so to say, of conformal field theories, and the deforming field as it follows here. And we will call them R1 and R2. So for what concerns the dual gravity side, the most general framework in which to derive geometries which are n equals 2 supersymmetric was analyzed in this nice paper by Gabella, Martelli, Passias, and Sparks. So they consider geometry with, well, of course, the most generic ones with an ADS4 factor, of course, and they are a work product of this ADS4 factor times an internal metric. So the way they derive this kind of geometries, or they specify them, is by demanding, of course, that there are two solutions to the variation of the gravitino equals 0 constraint, which is the usual supersymmetry constraint. And then in terms of spinor bilinears, they're able to provide these necessary sufficient conditions for the geometry to be n equals 2. And of course, these are a system of three differential equations with these quantities looking kind of ugly and built out in terms of these spinor bilinears. But luckily for us, we will be interested in a somewhat easier, or at least nicer looking kind of geometries, which are the ones for which the internal part takes preserves at least another isometry. So the line element takes this form, where here we have a Kähler-Einstein for manifold. And the nice thing is that now those sufficient and necessary conditions can be restated very nicely as a system of two differential equations for the metric functions f and alpha that appear here in the internal metric. They both depend on this coordinate r, which we will, with a misnomer, call in the following the radial coordinate, although we should keep in mind that this is an internal coordinate on this 7 manifold, and therefore is defined within an interval 0 or not. So it is not, properly speaking, a radial coordinate. And furthermore, we will demand that the metric on the Kähler-Einstein for manifold is the standard Fubini Studi on CP2. So that the isometry group gets enlarged to SU3, which is the isometry group of CP2 times U1 psi, where psi is this Reeb, the coordinate parameter is in the Reeb vector. So it's the U1 symmetry that any n equals 2 geometry should have. And then we have an additional, with this choice, U1 tau tilde symmetry, which shifts the tau coordinate. That is nevertheless not a full symmetry of the theory, because the 4-form flux breaks it. But anyway, here we see a partial reason for the title of our talk, because maybe it is not extremely explicit, but one starts recognizing the elements of the metric of a 7th sphere, for example, apart from these factors, and for the factors coming from the mixed product of this fiber and this psi tilde, we would have a CP2 factor and then have some sort of vibration over the CP2 factor that gives a 5 sphere. And then one can see that the metric of the usual 7th sphere, described as the join of an S5 and an S1, it's in this case a stretched and squashed because of these mixed terms and because of the prefactors 7th sphere. Let me also mention that this analysis carries so far was local, so one should find a way to promote these local coordinates to global ones, and we found at least 2 in the paper. But more importantly, of course, I wasn't completely entirely correct, because of course we should demand that the manifold has S7 topology, because of course these functions f and alpha are in principle still free to do whatever they want. But if we now demand S7 topology, demand regularity of the solution and satisfaction of some ADS-CFT properties, then the metric functions f and alpha obey some very specific boundary conditions next to the endpoints of the interval 0 and R naught. And these will be proved to be very useful for what follows. So by fixing the P, we see that we recovered 2 kinds of deformations of the ABJM theory from the dual gravity side. In particular, the P equals 2 Corrado-Pilch-Horner geometry solution can be derived analytically from this general framework described before by setting these values of the metric functions and of R naught. And while the cubic solution, so to say, that we would call GMPS, is unfortunately only known numerically. And here we derived it independently. So it was first derived in the same paper as before, by performing a Taylor expansion of FR, where R is this redefinition of the radial coordinate, next to R equals 0, and then using this expansion in order to trigger a numerical shooting problem. So by demanding the other proper fall off, so to say, of F, we are able to recover a nice parameter C and a nice value of R naught, for which the behavior of the F seems to be the correct one. And this is the behavior of the alpha as well. And our results agree, of course, with the ones reported in this paper here. Okay, so let me ask if there are any questions so far, because that was so far just the background of what we're going to do next. Okay, I can hear no questions. So let me quickly remind you, for those of you who are not familiar with this, what do we really mean by Kaluza-Klein spectrum? Because that's exactly what we're going to do. So let me take a baby example with a d-dimensional metric, which can be split in a d-1 dimensional metric, and then the metric of a circle, so an angle and of a certain size square. So for, in general, any field of the theory, but we will, for definiteness of this example, consider a scalar field, one could perform a Fourier expansion in terms of the eigenfunctions of this internal metric, which are the y denoted here so far. And of course, the eigenfunctions of the circle are just the harmonic functions. And then the Klein-Gordon equation for the massless fields in d dimensions reduces or implies a set of Klein-Gordon equations for the modes depending only on the external coordinates of the metric here, which are now massive when the mass is given exactly by this quantity here, and it comes from the derivative of the circle, and is parameterized by the number n, which will correspond to be the proper Kaluza-Klein rebel, and more importantly, is inversely proportional to the size of the compactification manifold. So what usually happens in a Kaluza-Klein reduction, one takes these dimensions to be very small so that the mass blows up, and the other modes, all the modes which are not massless, so they're not the zero modes, become extremely energetic and decouple from the theory. But in principle, and that's precisely what we're going to do, one could be interested, for reasons also for whatever reason, to compute the tower, the full tower of Kaluza-Klein spectrum, so to say. So the masses of all these modes and arranging them, organizing them in Kaluza-Klein levels. So that's precisely what we're going to do, but not for scalar fields, but for graviton instead, and on our generic, on our p=3 framework that we described before, instead of this method. Okay, so let's move on. Let's start this approach. We consider perturbations of the external metric, where here we mean the ADS4, and here we mean the stretched and square 7-sphere metric as before. And we consider that these perturbations factorize in this way with an internal coordinate dependent part and an external one, which is transverse and traceless with respect to the Levi-Civita connections of the ADS4. These perturbations, well, at least the external part, furthermore satisfies a Firth-Pauli equation, and therefore they can be really regarded as gravitons in a lower dimensional theory. These are the masses we're interested in, but then Bajas and Estes in this nice paper from 2011 showed that for perturbations of this kind, satisfying these solutions, the 11-dimensional Einstein equations reduce or transform into an eigenvalue problem, whose eigenfunctions are precisely the external parts of these perturbations, and whose mass operator depends on the details of the internal geometry at hand. So we see that computing the Kaluza-Klein spectrum for the gravitons, in this case, amounts to solving this eigenvalue problem with this specific form of the mass operator. Okay, so we have the mass operator, we specified to the case at hand, so for our geometry, and then we employ the symmetry of the solution that allows us to further expand the eigenvalue, the eigenfunction, in terms of eigenfunction of the S5, which we can reduce to the SU3 factor, and then eigenfunctions of U1, where with U1, I'll be clearer with what I mean by now later, we mean the diagonal U1 to these two original U1s from before. And then we have a leftover eigenfunction, which depends only on the coordinate R. We plug these ansatz into the original eigenvalue problem, and we get a set of ordinary differential equations for the eigenfunction psi, which are parameterized by the quantum numbers n and j, which I described here down. Now, what's the problem? Of course, the problem is that without knowing analytically f and alpha, there's no analytic solution to this problem. So the approach that we adopted took inspiration from this paper from Richard, Teresi, and Simpis from the 2014, that so it is a technique they developed and they used for a totally different aim, but it proved nevertheless to be useful to our case. Namely, we take as first step, given fixed quantum numbers, we solve the ODE because using the asymptotics of F and alpha that I mentioned some slides ago, close to the endpoints of 0 and R0. And this allows us to derive the asymptotic values of the eigenfunction psi close to the endpoints, from which we select only the normalizable ones. Then what are we going to do with these normalizable eigenfunctions? We use them as seeds to trigger a numerical integration of the full ODE, this time starting again for both the left end and the right end of the interval. So what do we get at the end? We get a set of eigenfunctions numerically integrated from the left and a set numerically integrated from the right. They both depend on the R coordinate and they are both parameterized by so far still free parameter that we don't know, which codifies for the masses. And then as a last step, we demand that for the physical values of the masses, so for the real, so to say, eigenfunctions that we're looking after, of course, the left and right behavior matches in the middle. So we are demanding that the two guys are linearly dependent, and these can be mathematically translated in the statement, and the Roskian, which is this quantity computed here, should be 0 in correspondence of the physical values of the mass. Here we denote it by a dot the derivative with respect to the big parameter. And that's precisely what we do. So here we plotted some Roskians. We see that there are always oscillatory functions which have several zeros, and that we will label by label k. So these, for example, will be the k0, k1, k2, and so on. And we can respectively show the plots for the numerically computed eigenfunctions in terms of in correspondence of the physical masses, of course, labeled by the same quantum numbers k. Then one could wonder whether this point the spectrum computed so far is complete, or whether we are skipping over any eigenvalue or any mass. But luckily, group theory comes to the rescue, because if we now think that the theory we're analyzing comes from an RG flow that starts from the maximal SO8 von Rubin ansatz, then what one can do is to technically branch the original SO8 graviton representations under the leftover symmetry group, namely SU3 times U13, where with U13, here I denote precisely what I meant before. So the diagonal subgroup of those two U1s, such that the values of the R charges are exactly R1 and R2, as we demand in one of the first slides. So we see this branching can be done. And now by a simple redefinition of the quantum numbers, we are now guaranteed to sweep over the complete spectrum, because by sweeping over the original quantum numbers, what we're doing is simply to travel through the whole SU3 times U1 representations of the states. So we are sure that we will recover all of them. So here's a table summarizing our results for Kaluza-Klein level 2, but in principle, one could go forever on by iterating the procedure. We have the Kaluza-Klein level, the SU3 times U1 representations, the degeneracy, the masses, the conformal dimensions, which for the gravitons are related to the masses through delta times delta minus 3. And then group theory also provides us with some insights about the schematic form that the operators should assume in the conformal field theory. Okay, so this is a good time to ask for questions, because we are approaching the final part. So if there are any, please speak up.
So you identify the dual operators in terms of group theoretical quantum numbers. That's
yeah, no. Yeah, of course. What I mean is, so for example, we know, I'll be clear about this, but I can start being clear from now. So for example, one can start branching the 8V, for example, which is the vector representation of the SO8. And that branches under under SU3 times U13, it becomes 3 plus 3 bar plus 2 other singlets. But we know that that split precisely corresponds to the split of chiral superfields that we made on the ABJM side, right? So we know how to properly assign the R charges. And we know, for example, that a singlet under SU3 should correspond somehow to a Z4 as a dual operator on the field theory side. While, for example, a triplet should somehow correspond to a ZA, because ZA are the group theory triplets under the ABJM theory.
Mm.
So that's what I mean. And then one can make further considerations about, for example, the arc charge. And that would correspond to see which kind of powers of this contraction of operators should we have here. Of course, this is still schematic because, as I said, you should get monopole operators and so on and so forth. But in principle, this is what I mean by group theory. It tells us the schematic form of the operators on the field theory side.
Yeah.
Okay. So I hope not to run too much out of time, but let me just mention very quickly that by inspection of this table, one can move some steps beyond the numerical results and get some analytic ones. For example, we see that there are some singlets. There's a tower of singlets whose R charge is an integer multiple of the R charge of the Z4, and N is the proper Kaluza-Klein level. And we saw that the masses are extremely well approximated by this formula. And therefore, by employing the relation between conformal dimensions and masses, we get a relation between the conformal dimension of these states and the R charge of these states, where Rn here is just R2n. So there are a tower of short protected gravitons also present in a similar analysis performed by these guys on the CPW solution. And as I was saying before, we know the group theory operator. We also know the correspondence eigenfunction because we know the quantum numbers of these states. So what we do, we plug these eigenfunctions into the original ODE, and we are very lucky for these gravitons because all the dependence on the unknown F and alpha factors out, and we are able to derive analytically the eigenfunction for this tower of singlets, and therefore the values, the rational values of the masses as well. So curious, I mean, this is just some plots to show that the agreement is very good between our ansatz and the numerical result for several values of quantum numbers J. And curiously, this is not enough because there is also a tower of octets of SU3 starting from Kaluza-Klein level 2, whose mass is very well approximated in this way. And therefore, by playing the same game as before, we derive that the conformal dimension is protected this way. Now, these states are not short, but as Billo and I think Frey and some others argued in a paper from the 2000s, despite not being shorts, these states have still nevertheless protected dimensions because they are shadows, so to say, of the massless octet at level 0. And what do they mean is simply that there's a hidden underlying relations if one computes explicitly the Dirac mass operators and wants to solve everything explicitly. There's a hidden relation between the conformal dimensions of these guys and the conformal dimensions of short states. So although they are not short themselves, their conformal dimension is protected. And these states are present also in the CPW solution. So one could play the same game as before. Now we don't get explicitly the analytic formula for Xi8. One gets an infinite set of ODEs parameterized by the quantum number J, which can be shown to be somehow reducible to only this system of two ODEs. And if now we pay some attention to the first of the two ones, we see that it is precisely the same ordinary differential equation solved by the metric function f. And so another analytic statement that we are able to make is that the eigenfunction for the octet should be proportional to the metric function f. This happens to be the case also for the quadratic deformation, so for the CPW solution. And here, by fixing this constant to 9/2, we see that the agreement between the numerically computed eigenfunction and the expectation is perfect. So this is a very interesting result that unfortunately I don't think I'll have time to explain. So let me quickly go on it. Basically, with these nice analytic results that we derived, we are able to prove by some sort of a reductio ad absurdum that this squashed and stretched 7 sphere is not trigonometrically embeddable in R8. And this is not the only case of compactification on such kind of manifold, because there's a non-normal mention for the famous squashed 7 sphere by Awada, Duff, and Pope of D83. I should mention that both solutions do not come from a consistent uplift from 4 dimensions. And as we'll see in some minutes, this is not the only features that they share, because one could in principle try to go beyond the graviton spectrum and make considerations about the full matter content spectrum of the theory. So given that the full symmetry group is OSP423 times SU3, where the 3 here denotes that this factor of U1 is contained without this OSP42, what one could do is to branch all the original SO8 representations under SU3 times U1. And given that the global symmetry group is this OSP42, one could try to arrange these states into OSP42 supermultiplets. Here I sketched the thing for Kaluza-Klein level 0. So technically what one should do is to group together all the triplets, group together all the octets, all the sextets, and see whether you can allocate these fields in terms of in a supermultiplet of OSP42. And in our case, differently from, well, this case of the similar analysis for CPW, it happens to be that this allocation cannot be made Kaluza-Klein level by Kaluza-Klein level independently. So here, for example, there's a persistence. I displayed a table for Kaluza-Klein level 0. And we already see that in order to complete, for example, a short gravitino, one needs to call or drag a triplet with spin 1 and another with spin 1/2 with proper R charges from Kaluza-Klein level high above in the tower. And this is the so-called space invader scenario for some sort of obvious reason, like they come and invade, and people in the 80s were very, I don't know, passionate about video games. And that's the other feature that the squash 7-sphere Pope shares, because there happens a space invasion as well, where I believe, if I remember correctly, they need to drag a singlet instead of a triplet in order to compute the massless graviton. Unfortunately, group theory alone is not enough to determine the correct invasion pattern. We have a lot of freedom. We provided some scenarios in our paper, but we have no definitive answer about that. Okay, so let me quickly summarize and end. What we have shown today is the numerical computation of the full Kaluza-Klein graviton spectrum over this M-theory solution, which happens to be the dual of the cubic deformation of ABJM. We were lucky enough to provide some analytic results as well. And these allowed us in turn to show that this internal metric on which we are compactified upon is not asymmetrically embedded in R8. And furthermore, the full Kaluza-Klein spectrum displays space invasion. But some interesting directions for the future would be, for example, to look for an isometric embedding for this manifold, because, for example, the squash 7-sphere from Pope can be actually be embedded in the quaternionic projective space. So what we have been trying to do, for example, was to embed our stretched and squash 7-sphere into CP4, for example, but without success. Another interesting thing would be to guess or to derive the correct invasion pattern, at least in a univoc way. But I don't see any realistic way of addressing this point without addressing the other two ones. And finally, let me mention what I personally believe is the most interesting direction to pursue in the future, namely to find or to prove whether there are any more robust links or connections between these 3 instances that so far happen to be just a coincidence in 2 cases. So the fact that the 2 11-dimensional theories do not come from a consistent uplift from lower dimensions, the fact that the compactification manifold doesn't have an embedding in R8, which is isometric, I should put an isometric here somewhere, and then the fact that the full Kaluza-Klein spectrum displays space invader scenario. So with this I conclude, and I thank you very much for not having fallen asleep. I don't know how many are still there, but thank you. So can you hear me?
Yes.
Please, if you have any questions, just go on. I don't know how in time I am, but
I have a very simple question. It was very impressive work, but the starting point, so you started from ABJM with k equals 1.
Mm-hmm. Yeah.
Why was it k equals 1?
The thing is, so why do we restrict to k equals 1?
Yes.
Yeah, the thing is that Okay, as far as I understood, maybe my supervisor has a more global picture about it, but a sure thing that I can tell is that for k bigger than 1, we start having some problems with these guys. Oh, sorry, I do not share my screen. Wait anymore. Let me share it again. So we start having some problems with the monopole operators.
Okay.
Because these monopole operators have a very specific form that actually depends on the Chern-Simons level that you are analyzing. Wait, let me share the screen again.
Okay.
I can be clear. So, for example, can you see my screen now?
Yes.
So, for example, I'm just making an example, but if k is equal to 3, for example, there's no way you can construct such a monopole operator with only 2 units of flux. As far as I remember, the lowest, so to say, monopole operator that you can build is one with 3 units of flux.
Okay.
I should. It's something we did long ago, so I don't remember extremely well. But this is for sure one of the problems, that these guys here are extremely fragile to manipulate. So for k equals 1, that we have no problems. We can even start from monopole operators carrying 1 unit of flux, and then actually building these guys from those guys, or starting directly from 2. We have plenty of freedom. But the more we go high with k level, the more problematic it becomes.
Okay. Okay. Thank you.
You're welcome.
Hey, sorry, I dropped out because my computer died. So sorry about that. I'm back now. Are there any other questions? Well, I'm not sure what I don't think I missed too much, but I have a question, 2 questions actually. About one is on slide 7.
Mm-hmm.
And I was just wondering about the solution that you have, the F there. And I'm just trying to get a better understanding what this is. Is the R0 a horizon for this solution?
Sorry?
The R0 that is written there, can I understand that as a horizon?
You can surely, I'm not sure you can understand it as an horizon. You can surely understand it as one of the points that becomes problematic for the functions f and alpha, because alpha always blows up in correspondence to the point 2. So in order to, well, here are the animations, but you make some considerations about the general metric, so to say. You want it not to blow up. And I think, for example, although alpha blows up with this behavior of f, you can ensure that this guy here doesn't blow up completely. So I'm not sure you can, I don't know how to answer very precisely to your question. I'm not sure whether you can consider an horizon or not. What I can tell you is that for sure it becomes one of the 2 endpoints of this coordinate here become the key for ensuring the proper behavior of these functions f and alpha, so as to ensure first that the solution has a S7 topology, and then of course that it is regular, so that it doesn't blow up in uncontrollable ways.
But in the structures, you have metric components that blow up if you're in the wrong coordinates. I mean, I'm
not providing any definitive answer. It might well be that you can regard r equals 0 as an horizon. It's just I do not have any more insights. What I'm telling you is that why the endpoints of this interval are important for our analysis. But in principle, I do not know how to answer very well.
Yeah, I was just interested in understanding better what the solution is, and what the dual field theory, like if it's a thermal field theory, for example, like this is the CFT with, which is thermal in a thermal state. So that's something that I don't see, but yeah, okay, that's just something to get an idea. For your symmetry, I think you first mentioned it on the slide number 8.
Yeah.
So you have the symmetry of the S5 there, right? I think it's SU3 cross U1 cross U1.
Sorry, is it slide 8?
Oh, maybe it's not on there. Yes, it might be a later one.
Yeah. Anyway, you might.
So
Okay. Maybe I know what you mean. Wait. Maybe I know what you mean.
Yeah, here's the example where you just have to circle like a U1.
Yeah. Precisely.
Like an S1, and then you went and generalized it to the full structure, right? SU3 cross U1 cross U1.
Precisely. You mean here?
When you have the full harmonics, spherical harmonics.
Yeah, you mean here.
And so in order to maybe to simplify this, and maybe you thought about this, but would there be a possibility to, so if you think of this as some sort of angular momentum algebra, and you would think of the two angular momenta on the S5, or two charges on the S5, do you think maybe what one does in rotating black holes is to set, to simplify the cases, to set these charges to equal to each other. And so I'm not sure if you worked on that and have maybe like an analytic, maybe it's easier, I don't know, if there's a possibility, because then you reduce the symmetry, I think, to SU2 cross U1. And I believe in that case, your spherical harmonics turn, like the Y's would simplify, but I'm not sure.
No, yeah, I mean, sure, but what I'm dubious about, well, doubtful, I don't know, is that we do not really want the symmetry to reduce further, because we want to preserve the field theory interpretation of the dual of a cubic deformation. So for the cubic deformation, you need the SU3 because you have the three chirals which are rotated into each other. So yes, it might well be. I mean, I'm sure one can play a lot with this kind of geometry, still getting very interesting physical results. It's just in order to preserve the field theory interpretation of a cubic deformation of ABJM, I think we do need to preserve the SU3. But your idea, I mean, your idea is interesting. I'll actually, do you mind if I write it down? Or
no, go ahead. Like it's not that I don't claim that all my ideas are great, and I'm surely not able to follow.
It's just confidently, I would say that you lose the field theory, at least dictionary, so to say. Maybe not with the geometry, but at least with the things you're doing.
Yeah. You guys had a different goal. Yeah, I understand. Okay, I should ask if there's any more questions right now. Okay, if that's not the case, we're running a bit over, but that's we started slightly late. And,
sorry about that.
No, that's not you. That's not you. That's us. All on us. We're still within time to start at the correct time for Gabriel. So that's all good. So I'm going to stop the recording right now. Wait, I cannot. Somebody is who is the host right now? Gabriel, you're the host. Can you could you stop the recording, please?
How did I become the host?
Because I dropped out.
Stop recording.
Okay, I'll just stop sharing then.